Yeah, if that was 0. That's a good question.
And it can be anywhere, right? Does that be
Well, we wouldn't worry about it if it's on the tails, because
Yeah,
there will always
just
be a
like
0, but if
anywhere.
it's in the middle anywhere and there's a gap in data, we would note that.
Isn't the tail like basically the same as that? Some people just how it's skewed left. It's like they both drop down. Like,
No, that's
But
oh shit.
But if you really look at it, it's
I would say, do you see how the majority of that data is further right?
Yeah.
And so the tail would be all of this really, whereas this is really only the tail. Notice if I were to draw a roughly, or a smooth curve, you see how that's symmetrical? That is not though. Does that make sense now? And that's one thing, notice I'm not going to draw the curve going over every single bar, I'm going to draw a roughly smooth curve. We'll see that more in the next lesson. Excellent questions throughout though. What are your questions before I continue? Guys, don't forget, get involved in that conversation, actively collaborate
Oh, that's what that's.
in whole class discussions.
Yeah, a little free in here.
Yes,
makes
and
me
Max.
really like.
I can fix that if you want to continue bragging, Madison.
This is a really like great question. Like, can it be bimodal and symmetric?
Mhm.
Okay.
Look over there at that data set. Right, your last one on the random number generator, that was bimodal and that's roughly symmetric.
Because it's two humps even.
Huh?
Two humps level.
Well, it's not just because it's level, it's because if I were to draw the mean, doesn't it look about the same on either side? That's what symmetry is,
Oh.
right? Symmetry is that it looks roughly the same on either side. Mel Bourdier.
Is all of them going to be either like bimodal or,
Say that one more time.
is either like, is all of the ones that we're going to look at, like, are they going to be like either like, roughly symmetric or symmetric and bimodal? Like, does all of them have to have like bimodal?
Do they have to have bimodal?
Like,
Either or.
I mean,
either, that she's saying symmetric.
here's the thing. Here's the thing. I'm never going to assess you on something that we haven't covered, but like, I mean, if I were to give you something like this, how would you describe that?
Trimodal?
Trimodal, three-modal, multimodal, I don't care, but like, it's straightforward, right? It's unimodal because uni means one, bimodal because it means two, right? Don't stress that. But also, I'm not going to assess you on things that I haven't talked about in class. But the majority of data that we focus on is unimodal and skewed or symmetric. Okay. So I want to point out, number 5, do we have a different number of cell phones? This is just the next question. No. Same number of cell phones, 10,000 hours. What's the difference this time around?
1 hour.
Yeah.
Is it 1 hour?
Wait. No. Yeah.
It's a tenth of an hour is my, and I'll go ahead and tell you the name for that, the bar length is called a bin. So if you hear me say bin, that's just talking about how the values in between here, right? So the bin here would be 9.5 to 9.6, 9.6 to 9.7. Those are the bins. So they decrease that bin width, right? A tenth of an hour instead of half an hour. Compare these histograms with the histograms from the previous question. How does decreasing the interval size change the appearance this time around? So again, I need you to hear me. This is exactly the same data you just looked at on the previous page. So how does changing the bin width change the appearance? Talk about it within your small groups for a couple of minutes. We're going to come back together and have a whole class discussion. Shade. Read the question. Shade. The question in the book.
Yeah, you're right.
See, Samaya, Key, Anthony talking about it heavily. I need all 4 of us talking about it heavily.
Yeah, come on, because there's some bar.
What is it? There's a bigger gap.
Yep. Does it? What do you see when you draw your smooth curve over there? Yeah, look at the new one versus the one before. What did we say when we looked at the previous graph? Talk about it. There's something you're forgetting.
Yeah, they're roughly.
I was saying, he doesn't look perfect, but one thing is you don't want to ever call it a straight line. It's a nice smooth curve. There's nothing else that's different about the shape. Go look at the previous graphs and come back to right, because that's what it says. But we decrease from half an hour for the relative frequency to 1/10 of an hour. Thank you. Thank you. Thank you. So let's bring it back. Let's have that whole class discussion. People get involved in this conversation. We're gonna have lots of things going on. I need to hear from some people I haven't heard from at all today. Come on, so let's get some volunteers in there. I've heard from like all 4 of you. Thank you too. Okay. I haven't heard it all.
Both my hands up.
I haven't heard as much from Key Anthony. I'll give him a chance. But like, hold on, pause for a second. I need y'all to remember, okay? I want y'all to talk and I want you to engage, but not to call them out, but group 3, have I heard from any of y'all today? Sorry, just like blinking like, shut up, Mr. Kenny. Guys, I want you to actively learn. The more you talk, the more you learn. The people who talk the most learn the most. Get involved in that conversation. I know that some of us are shy. I know that it can be scary at times. And I know that we may not want to do it, but I'm looking out for you. As a person who absolutely is an introvert to the core of my being, who has had to battle against that because I learned, man, I got to talk with people for the rest of my life. It's beneficial to get that practice in now. My teachers forced me to do it, and I am so thankful that they did. So, don't forget, it's okay to even make mistakes. I praise those things. I encourage you to share out whatever you have, and we'll add on to or push back on so that we can all grow and learn together. Just what are you noticing? So someone I haven't heard from yet. There we go. Thank you, Devlin. What you got, sir?
This seems more symmetrical than my trash.
Okay, this seems more symmetrical than the last. Does anyone want to add on to that or push back onto that? All right, Destiny, what you got? Sweetie, you can't get upset when I've called on you multiple times today. Chill, girl.
Exactly. You gotta be done and get a box.
Which one's skewed more to the right? One at the top, okay. Interesting. Anybody want to push back or add on to any of that? I did see JC's hand up first. I'm going to give her a chance.
Okay, so with both of them, there's gaps in between.
Okay, so I want to pause, and there's a couple things I have heard at this point. I got to ask, and I need to emphasize this, I need you to pay attention. What is this question asking us to focus on?
The person in
The appearance, right? Yeah. What component are we looking at with appearance? What of the 4 pieces where we analyze data? Shape. Gaps, 100%, right? We're going to see more gaps when we decrease that bin width, but don't forget we're focusing on shape. Where do gaps come in?
the end.
Unusual aspects. There we go. Gaps in our data are all about unusual aspects. Okay, so focus on that. But I saw some students doing this, and I want to emphasize this is a good call, right? Nice, smooth curve. Okay, now it does look like that right tail is a little bit longer, but still overall it's roughly what? Symmetric, okay? I know some of us had more things to add, but we gotta keep going a little bit. So here, how does decreasing interval, both distributions are roughly symmetric now. So I want to point this out. I need y'all to pay attention to this. Does it matter how long your interval length is, or interval width is?
No.
Wait, I thought we just said that this was,
Yeah, it matters.
I was saying, this was skewed left slightly, right?
Yeah, that matters.
Whereas now this is roughly symmetric, right? So that interval width does matter, and I'm bringing this up because what we're going to study is something called the normal distribution. You want your data to be roughly symmetric, okay? So change that graph around at times change that bin width so that it is roughly symmetric. Okay, so the interval width does matter. The bin width matters. All right.
Sometimes I think you do ask some trick questions.
Okay.
I thought that was a yes.
You thought what was a
I thought
yes?
that was, I mean, I thought the answer was no. I'm not gonna lie.
What was no?
The answer, the question you just asked.
Which question did I ask?
I don't remember.
I was like, I asked a lot of questions. I don't know which one you're talking about. Sorry if you think it's a trick question. I'm trying not to make trick questions. Focus on our vocab sum. Okay, so really quickly, because this doesn't, hey, please listen, this doesn't heavily influence us moving forward. Number 6 says explain why the scale of the y-axis changed when the interval size decreased. Well, if you have a smaller interval width, you're going to have less of the data in there, right? So the relative frequency is going to what? Decrease. Remember, I think it was from 10 to 10.5 earlier, right? If we add up all those relative frequencies, it'll probably get us up to that 0.37 that we were seeing earlier, right? It was half an hour. Actually, let's look again. 10 to 10.5. Yeah, okay, so 0.35, right? And so that's what's happening is if you were to add up all of these, you would get about that 0.35. But because I'm now splitting that 0.35 into those 5 different intervals, well, it's a lower relative frequency. So I had to change my y-axis, okay? So why is the scale of the y-axis different? Splitting each bin into 5 bars simply lowered relative frequency. Simply lowered relative frequency by splitting it into 5 groups. That's all it is. That's just a thinking question. That's not critical to understanding stats or anything like that. It's more about understanding, hey, I just want you to think about it. If we have 1 group versus 5 groups, that's going to lower it, the relative frequency because we're splitting it up. Yes, ma'am, Tori.
What did you say bin was?
So bin is the interval, right? So the bin is the interval for that bar. Yeah. And you literally just spell it as B-I, oh yeah, I already have a speller there. So the bin, that's the interval for each bar. I'm burning marker. All right. Ready to continue?
Shut up.
So this is what the whole point of all this was to get to. You'll notice, hopefully, that these are rough curves, smooth curves of what we just saw. Okay? When the shape of each relative frequency histogram starts to resemble a normal curve. All a normal curve is a bell-shaped curve that is symmetric about the mean of the data. Why do you think they call this a bell-shaped curve?
Because it's like a bell.
It literally looks like a bell, right? We're not being fancy with it. If you look at that shape, it kind of looks like a bell, okay? So it's a bell-shaped curve. A normal curve models a theoretical data set that is said to have a normal distribution. You see that word right there, theoretical? No data set is actually a normal distribution, but we can get data sets that are close. No data set is actually a normal distribution, but we can get close. That's why it's called a theoretical data set. And the theoretical normal distribution has lots of uses. All right? And so I do want you to note this comment right here. Normal curves can be narrow or wide, but all normal curves are symmetric about the mean. And I will point out, is it unimodal or does it have more than one mode? It's unimodal, right? Normal curves. Right? Unimodal and roughly symmetric. It's got to be bell-shaped. And in order to be bell-shaped, it's got to have those two pieces. I would circle that boxed note as well. The vertical axis for a graph of a normal curve represents relative frequency. And sometimes if it's real data, you'll see that y-axis, but a lot of times normal curves are just shown without it. Because I will also point out, remember how we did dot plots earlier? You don't need a y-axis with a dot plot because they just stack on top of each other. Right? So you don't always need a y-axis for the normal distribution. You need it for histograms, but you don't need it to draw that approximate normal distribution. What are your questions before we continue? I know some of y'all are still writing, which is why I'm waiting, but for those of y'all who are not writing, what questions do you have?
We need to see the following students in the office. I need to Honoria Adams, Lindsay Atkins, Michael Alford, Javante Hall, Nathan Carroll, Ayan Shaver.
So what makes this not normal?
Austin Gray, it's
Bimodal?
Maria Hood,
Skewed right?
Jordan Stevens,
Okay.
Hayden,
So we want to recognize that.
again,
Alright, so moving, I don't know why I have that one slide in there twice. Okay, so we're on to activity 1.2, that's skip number 1. Hold on. No, keep going. Apparently I skipped question 1. Oh, I know why. I didn't mean to skip it, but I did apparently. I originally wasn't going to cover it. It is time for us to learn some math. That's what time it is. No, stats, sorry. My bad for lying to you. It's time to learn some stats. Ooh, Mr. Kenny, that's so exciting. Mathematical science. Alright, I don't know why I accidentally deleted this slide, but here we go. So, notice we already talked about mu. We've already talked about x bar. I will point out this detail. We talked about standard deviation. Sample mean. X bar. Remember that's sample mean.
And then the other one's population.
Mu is population mean. S, what is that going to be?
Standard deviation.
Yep. Sample or population.
Are these like little things to be able to learn it?
If you look up here, it says S is, hold on. Nope. Standard deviation of a sample is the variable S. Alright, so sample standard deviation. That's a normal approximate or abbreviation for standard deviation. And it talks about this Greek letter sigma. It's a different sigma, it's a lowercase sigma. It looks like a circle with a line, but that's the lowercase
What's
sigma.
the uppercase one?
The one over there with X bar. Remember this sigma? That's the uppercase sigma. Just like we have lowercase and uppercase, they just have different symbols. Because Greek letters are very different.
Is this going to be on the learning check?
How about we just learn it and wait to see?
I would want to know if it's on there or not. You will need to know the different symbols. If I use that symbol, you need to know what it means. Now, the reason why I am emphasizing this, though, is because we talked about the difference between a parameter and a statistic last week, just briefly. Does anyone know which of these would be statistics?
Wait, which one?
S might be.
All of them.
They're not all statistics, only 2 of them.
Oh, simple. Yeah.
What makes these 2 statistics? They're samples. Statistics are samples that allow us to make an estimate of the, what's the P word I use?
Population. Is that what it is?
Parameters,
True.
right? Notice statistics approximate the parameter. And so the statistics come from the samples and they approximate the parameters, the population values. What do you mean? Well, let me ask you this. If I have a sample and the sample mean is 7.6, what would you guess the population mean might be?
8, yeah.
I would have assumed 7.6.
Well, that's the sample.
Right.
Oh, I see what you're saying.
But it's supposed to approximate or estimate,
I
right?
don't get it.
Okay? Huh?
She said.
If I got a sample, right, and the sample mean was 7.6, what do you think the population mean might be?
7.6.
7.6.
Because like the sample is the population. Well, not is.
It's
but it
representing, hopefully. We're going to talk more later about how to get a better estimate. But the whole thing is that a sample is supposed to be close to a population. Okay. All right, got a good 5 minutes left. Good 5 minutes of learning. So, yes, sir. So right here, I want you to notice this. Right? Remember, a standard deviation is a typical amount that values differ from the mean. So if my values are really close to the mean, is that normal curve going to be taller or shorter?
It's going to be taller.
It's going to be taller, right? It's going to be a higher relative frequency, right? So if it's really spread out, the graph is going to be shorter, right? So when I look here, right, we have normal curves A, B, and C represent the battery lives of a population of cell phones with comparable models from 3 different companies. The normal curves represent distributions with standard deviations of 0.1, 0.4, and 0.5. Which of those do you think would have a standard deviation of 0.1, a really low standard deviation? C?
A.
Why is
I'm
that?
thinking A. Because
See,
it's
you
tall.
guys know.
You guys stop doing that, Mr. King. You don't make me think. JC, what are you thinking?
I think it's C.
Okay.
A would be 0.5 because it's the tallest.
Okay. Okay. So anybody want to push back on that or add on to that? I don't know, Mr. Kenny. Hey,
I think A is 0.1 because B and C are very close to each other, and so are 0.1, 0.5.
okay, so that might be some logic, but I want to go back to what I just said about standard deviation. All right, so think about this. If the data is really close to the mean, notice I don't see the actual values down here. If the data is really close to the mean, then the relative frequencies at the mean are going to be taller, which means there is less variability, there's less spread. The taller it is, the more compact it is with less spread. Does that make sense? So I see your reasoning on that. That was a little bit of a way around the reasoning, the 0.4 and 0.5. But again, the taller it gets, the more it's going to be around that mean. That means there's less spread. So higher curve, right, equals less spread. So sigma equals 0.1, which might make us think that B is what?
0.4.
Sigma might be 0.4, it's a little bit taller than C, so C sigma equals,
0.5.
right? Okay? But I don't want you to forget, like we're writing out, we're approximating, we're just identifying, hey, the taller the curve, the lower that spread is, the lower the standard deviation. But what do we mean when I say sigma equals 0.1? What does that actually mean? Say again? Say a little bit louder. The sum. So there was something with a sum earlier, but there's more to it than just that. The sigma, the standard deviation equaling 0.1.
Population.
It is a population standard deviation. But guys, what does standard deviation mean?
Typically, how far back is it?
So typically, values in this data set differ from the mean by how much? 0.1. Typically, values in this distribution differ from the mean by how much? Okay? Typically, values differ from the mean by 0.5. That's all we're saying, right? It's a typical amount by which the values differ from the mean. Okay, so we'll wrap up this lesson tomorrow and start on the next lesson. So just so you're aware, okay, Module 5, Topic 1, Lesson 1, practice numbers 1 and 2 are due on Wednesday. Okay, so that's the lesson we're wrapping up. Those two problems are due on Wednesday. You got 2 days to get it done. You can knock out one problem today during enrichment. You can knock out one tomorrow during enrichment. No excuses. No. Hey, listen, pause and listen. This is the very end of the lesson where it says assignment on page, I should have put the page M5-17. This is on M5-17. You'll see a section that says practice, numbers 1 and 2. Be aware that it does go on to the next page. Okay, so it's M5-17 and M5-18.
Keep that up to the bed where so I can put it in my notes.
Oh, God.
Let me see the picture. You plugged it to me already. I feel hurt.
She just said what?
If you want,
She said what?
you want to take a picture, there it is. Have a great rest of the day. I feel like some good learning was happening. Let's get some more people involved in conversations tomorrow. Right, Colin? You'll be involved in that conversation. Right, Zaria? You'll be involved in that conversation. Yes, sir. That's all I hear. Thank you, Leah. Look, my own way.
It ain't nothing like that.
Class again. I'll try to re-explain it a different way.
Just bring that. What happened to you?
The standard deviation part.
Yeah, I didn't get that either. I don't know if it's a little.
This?
Yeah, what does that mean?
That's the Greek letter sigma. It just means sum. Like, huh? All your x values. Right? 3, 7, 10, 11, 12, 22. Right. A sum is just adding. You've done means in the past, right? You just add all the values, divide by how many values you have. So that's literally what, this is a symbolic version of that. Sum or add all of your values. Divide by the sample size.
Dang, y'all still.
So remember that came from here, right? Again, what does this symbol mean? So it's going to put, that's what it is, but it means sum. So I'm going to add all of these differences squared. Okay. You add all these. Right. That you got to know that that symbol means to add. N is the sample size. So we had 1, 2, 3, 4, 5 of them. 5 minus 1. Okay. That's not during the whole class. Here.
I meant to snatch.
I said thank you.
You said thank you, but you still snatched.
But it wasn't a mean.
It's all about that attitude, though, girl.
It wasn't a mean snatch. It was just a snatch.
I mean, is a snatch ever nice?